Welcome, welcome, welcome to the stream. This is Jason Watts, AE, your friendly neighborhood automation engineer. And it's been a couple of minutes. And so if this is your first time joining in, welcome to the stream. A little bit about how this stuff works is, we're gonna go through a couple of different topics. Then at the end, we will go through kind of like just chat and talk about automation stuff, whatever's coming in. Hey, Lucid, you definitely watch out. So a new little feature, if you're here live and you're actually on the stream, there's actually a competition for who can chat the most. So right now, Lucid, you are in second place, and you're in second place, and Mika is in first. So you have to chat it up and like get to the #1 top stream. So a couple of cool little things that YouTube's been putting in to try to get the community together. We've got an actual new member that just joined. Welcome in. And we do have memberships, and one of the things about the memberships that you get, all of the content that we do on this stream, I'm going to make available to the members at the programmer level. You actually get this block. You can play around with it. I'll probably put in some sort of like disclaimer about, hey, I'm not going to tell you that it actually works, but it gives you a great start. You'll get the programs. So the programmer level members will get the actual archive of the program that we're working with today, and the kind of supporter levels will get the block. So you'll just get a library with that block in it, so you can import it in and play around. But the highest level, programmer level, they get access to that. But anyway, without further ado, today we are talking about the HART programming interface. And if you are not familiar with HART, it's not this, it's HART. And I had it pulled up here in the little, the manual. And it stands for, HART function stands for Highway Addressable Remote Transducer. It's fancy. Really, it's an analog input. So you got your 2-wire 4-to-20 analog input going out, and there's a communication interface that stacks on top of that, and you get extra variables. If you, any working in the process industry, working with kind of pressure transducers, level transmitters, these sorts of things, it is a way to communicate to your, wow, all right. If you're watching this on YouTube after all of this, you'll realize that I edit these. So the first part, we get the stream going, welcome everybody in, and the last part of the of the stream, I trim off. So, and then give it to the members. So the last part that is a members only section, if you're here live, you get to participate in it, you get to watch it. That's kind of the chat. You can ask questions and I'll kind of freestyle that. But the main content for today is talking about these HART sensors, and going from there on it. And so I will edit off anything off at the end, and this little section where my battery died. So you didn't see that if you're watching on YouTube. So let's get going on this. So the HART function for these modules is a pretty cool little thing that honestly I had I'd heard about it, but I just started like seeing the kind of need for it when we're kind of doing these larger plants, because some of these things, like for flow transducers, for example, you'll have a flow rate and then a HART secondary variable that is like a totalizer, for example. Some flow meters will have a totalizer, and so it's like, all right, your total number over a certain amount of time, you can get that data over HART, and that is very much beneficial. I'll put it that way, because it's not as fast, because it's having to kind of do a little bit of a communication, but you can still do some pretty slow process control, or at least some data logging and things like that with it. So that's what we're going to be talking about today. And in the Siemens world, the way that we're going to bring in this HART technology is through the ET200SP analog input with HART enabled functionality. Now this analog input is considerably more expensive than the regular input because technically you're able to bring in a lot more variables, a lot more stuff. And so you're really kind of doubling your ability for all of this stuff. Whatever. My camera seems like it might be a little too low, but whatever. The analog input module with the HART functionality, you get 4 extra variables, 4 channels. So you kind of turn a 4 input module into kind of a 16 input module. And we'll talk about that here. We're going to go through just about HART. We'll talk about some of the ways that it interfaces, just a little overview. And then we're going to talk about the actual hardware that we're going to be talking about. And that's for this project. It's a VEGA Puls C21, and it's kind of their mid-level, VEGA's mid-level transducer. And then we're going to be using the ET200SP HART interface module. We'll go through the portal and how to actually set all of that up and kind of get you going there. Then we will go through the actual HART block that I have come up with, and I put a lot of pain and suffering into this block because it was not simple, and I'll show you why. And I'll go into probably more of the details of what was going on with that block if y'all don't have any questions in the kind of members only section. So without further ado, let's talk about HART. And I'm gonna flip over and let Siemens talk about HART. I'll keep talking, but yeah, I will. Let's see. Do I have my video capture device? Am I here? Hey, look at that. I'm here. So what we've got over here is the ET200SP manual collection, and it is the rule all manual for ET200SP. It's big, it's bad, it's got everything in it. And as you can see, I have pulled up in it the HART module, and I've gone down into the section of the HART module. And now this manual has every ET200SP module available. So you've got everything from digital inputs, digital outputs, analog inputs, technology modules, which, oh, by the way, I'll show you this real quick. A workbench. Look at that. Hey, we've got real I/O, we've got real stuff. And if you can't see, that is the ET200SP module is there far off to the right of your screen there. And I've got a little 1500T PLC. You obviously don't need the T PLC, but I've also got a bunch of other junk on there. Don't mind all of that. But we've got the HART module is the one farthest to the left. So it kind of looks purple in this, but it's got kind of like a dark blue square. And then you have the Siemens blue square to the far right of the ET200 rack. That's actually a technology module called a TM position. I think it's 2 or 1, but it's actually a position input. So like an encoder module. And won't talk too much about that, but like right now, but it actually has a hand wheel hooked up to it right now. We might talk about that in the bonus section. So if you're seeing this and you're like, what bonus section? You're too late. You either have to be a member or watch it in the first week. So yeah, so we'll catch up on that. But we're talking about this module, the HART input module, and it's going to be on the right. And it's that kind of, like I said, it looks purple, like the little input there. If you haven't seen a ET200SP, we use it all the time for our stuff, and I think it's pretty stinking cool. That module or that system is very robust. You have a lot of different options for the actual head units, so you can connect up with different feature sets in those. But then obviously all of the different I/O modules, and they are expandable up to a lot. I think the high feature can do like 64 modules or something, maybe 128. I'm not sure. I don't really know. I don't know the Siemens stuff very well. Oh yeah, I didn't do my little introduction of like who I am. Oh dang, I guess y'all don't know who I am. I'm Jason, by the way. Hi, nice to meet you. Um, yeah, this is what I get for not streaming in over a month. I forget how to do all my intros. But let's go back to the HART module, and I think it's the sketch ad. 64, yeah. So Mika's helping out. 64, I think is what it is, and honestly, 64 input modules would like take up a a lot of space. So you're probably not going to be able to physically get much more in there. I will say, just kind of an aside, if you want to make your panel builders and your electricians out in the field absolutely hate you, shove too many of these IO modules into a small box. What you can get a lot of IO into like a very small space with these ET200, and then you realize, oh, if we actually use all of this IO, there has to be terminals that land somewhere. And so we at Alpha Industrial Technologies, we always bring our IO off the module out to terminal blocks to just kind of give the electricians a break. But when you have goofballs like me and put too many IO points into too small of a box, I get death threats by my electricians. But yeah, so be sure to remember that it's tight in the form factor, but it's a lot of IO points, and if you're bringing those into the field, usually you're going to be bringing them in. And just remember, we're laying those out. And I did a panel building topic, and I think I touched on that sort of thing. But we went through all sorts of stuff of how to like design an actual panel, and that definitely is one. So let's get back to this HART. How does actual HART work? If you have been in industry for very long whatsoever, you will have experienced a analog input. And I could bring you this one over here. Hold on. I'll walk back and show you my little HART module. I meant to bring this over here earlier, but this is our actual level transducer. And you may have never actually seen one of these, so that's why I realized I take for granted. I dropped my paper. Not everybody has running on 25 years of experience in the industry. So wherever you're starting, this is a great place to be because we start from the ground up. And so this is a level transducer. And right now I'm looking at my level and it is going all over the place because it's supposed to be like this. And this is taking and shooting out radar. And this particular radar sensor is of a frequency that can penetrate through kind of like some dense solids and everything. And this is really good for dry, kind of dusty environments like that. But it only has 2 wires that actually come out. I guess technically there's a shielding ground on it, but you have 2 wires that come out, and it's a 4 to 20 milliamp transducer. So this will, depending on how you set this guy up, this will output either 4 to 20 milliamps, so 0 to 100%. And the reason why you have 4 to 20 milliamps is if it's 0 milliamps and you're reading 0 as 0, then you don't know if that's an open cable, like you have a cable break, or if it's actually 0% and it's still working. So that's why you have that 4 milliamp offset. So you can also go below 0 as well. So you can do like a 3 milliamp and it will actually read below 0. And if you ever read 0 milliamps, you know that this either isn't powered or you have some sort of break or some sort of issue. But this is the level transducer that we're using. And like I said, I'm looking at the actual level right now over on my TIA portal, and it's kind of going crazy. So I've done messed it up somehow by doing all this, but we'll figure that out later. It's not really the heart stuff is still doing all right. So what HART does is it takes this normal sensor that is 4 to 20 milliamps, and it then takes and puts on top of it a separate set of signals. So as you can see, you have your analog signal that kind of goes across here. And let's see if I can get this going. So this is your 4 to 20 milliamp signal. Let me put this up. Maybe not. But not gonna hold my breath. So we have our 4 to 20 milliamp signal here, and whatever it would be reading, it would be reading. Oh, it actually started working. Sweet. So right now it's reading at like 70%. Yeah, that looks like 70%. So the way that this would look is there is a signal that is kind of like this. And this did this earlier, and it's annoying. So this signal could kind of go across, grow across like this. And what HART does is it puts a secondary signal that gets interpreted as a 0 to 1 based on the frequency. So you can see here that this sort of signal here is, if it's 1200 hertz, it gets interpreted as a 1. If it's 2200 hertz, it gets interpreted as a 0. Just know that it's taking your analog signal, the average, and then putting a signal on top of that average, and being able to decipher digital communication from that. So pretty cool stuff. And that's kind of what we're talking about today, is this analog signal. So again, you don't really have to know how the HART system works. You really just need to know how to set up the input card, how to set up your device if it needs to be set up for HART for something, and then you just need to know how to use the data and what's available. So one of the things about HART is that it is pretty configurable, and we'll go through, and most HART, by definition, I say most, it is by the definition, you get 4 variables. And yeah, so Nathan, it is very much like FM radio. It is taking off that modulation, that frequency modulation, and pulling out digital signals. So, and yes, eventually we will, this is a motion control channel, but try to reach out. We'll do some stepper motors, stepper drives. If you did not know, there's in chat, someone's asking about stepper motors, by the way. If you did not know, the 1200 PLC has built-in Puls stepper control built into it, just so you know. So low end motion control is available in the 1200 for stepper motors. But back to HART, you have 4 variables that by definition are available. So you have a primary, a PV, a secondary, an SV, a tertiary, third, and then a quadriary. So P, primary, secondary, third, and fourth. So quad. So you have 4 variables. And on the device side, so the actual level sensor or whatever, that is kind of varied. And so what you have to do is you have to bring up your actual device variable, or sorry, your device manual, to say, okay, what by default are these variables? So your primary, secondary, third, and quad. So primary, secondary, tertiary, and quadra, whatever. It's some weird quad thing. So you get that information from your device. Now, just so happens this VEGA Pulse level transducer, you can actually select what those devices are, and we may do that later. I might play around that in the bonus section, but it's not really necessary to know up front. You just need to know, all right, digging through all of this stuff, where do I need to actually find this stuff? So go through, and eventually you will be able to find somewhere where it says something about the HART variables and what they mean. Sometimes these can be hard to find, and honestly, I probably should have written down on my piece of paper here what page it actually was on, because the HART variables by default are on this one is blah 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 blah. Like I said, they're variable, but you have the ability to, or by default, man, I'm gonna embarrass myself like this by not knowing where my VEGA sensor documentation is. But anyway, so we can go through and anyway, whatever. It's in here somewhere. Eventually I might go off screen and just be talking and find this, but just know that you have 4 variables that are available to you on this. And like I said, on this VEGA Pulse, it's set by the device itself, and you take your cell phone, and it's got a Bluetooth connection, and it's got an app called VEGA Connect, and you can connect up to the sensor, do all sorts of stuff. The Pulse 21 has a really cool set of features. For example, remember I said that you could kind of ground penetrate, like it can shoot through things. So if you have a product flow that you know is flowing through, and your sensor is sitting up and you have a product flow going through, you can actually say, hey, I know that there's product flow here, so shoot through that and actually detect the level down low. So these are some pretty cool stuff, and you could set all of that stuff up on through the VEGA Connect app. So that's VEGA, that's my plug, lots of stuff there, check that out. But this is a Siemens channel, right? Actually, it's not really, it's really an automation channel, but I don't like other vendors. I don't know nearly as much about than Siemens. So let's get back into the things that I actually know. So one of the things about this HART module itself is, if you're not familiar with kind of the way that you wire up the module itself, it can kind of get a little bit difficult, because there's all sorts of different ways you could wire this stuff up. And so this is not wired up in the same way as like your standard analog input. I think I've got a couple of these laying around here somewhere, but it does not wire up the same way that a standard analog input is wired up, because normally for the 4 to 20 milliamp setup, you're set up on the top for just your standard 2 wire. You're going to be on 1 and 5, 2 and 6, 3 and 7, 4 and 8. Like, those are going to be your 4 channels up for that 2 wire. Well, in this case, it's actually down below. So your 2 wire transducers will actually get connected up differently. So you're going to be, so this MU, so this 1, so you're going to be between 9 and 13, 11, 15, 10 and 14, 12, and 16 for the actual 2-wire transducer, the 2-wire connection. They get shifted down to the bottom terminal. So just be aware of that. All this other stuff that's built into this, you don't really have to know unless you're using one of these HART devices. You can go in and look at the HART data, because this is like a complete communication bus that's on top of this analog input wire. So you don't need to know about all of these, like the ohms and the resistors and termination and all of that stuff in there. That's built into the module, built into the system. So one of the things that we do need to talk about, though, is once you get that stuff set up and that stuff hooked up, you will automatically have a signal coming into the module just the same as you would before. So you're going to automatically have that analog input 4 to 20, and you don't have to touch the HART stuff. And so it comes on your level sensor, depending on how you have it set up, the range and everything on it. Depending on how you have that set up, then you're going to be able to automatically bring that value in. And I'm going to show you that here in a second on NTIA Portal, because we're about to jump into how do you actually set this stuff up. And so just trying to think of anything else that I want to show you here. How hard, that's all that, blah, 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 blah. So just a little bit about how to actually grab the data from this module. So your 4 variables that you can get, there's kind of 2 different ways that you can get data from an input module. If you are aware, there is usually a lot of extra data on input modules that doesn't show up in your standard address area. So in your process image table, it doesn't show up. And all of that data is stored in what is called data records. And with this HART module, you kind of can have your cake and eat it too. But so remember, with this 4 input module, we're going to have 4 variables per module. So you'll have 16 HART variables that are available that is getting communicated back and forth. Siemens, instead of saying, okay, this is going to essentially take up 20 analog values or more, it said, okay, we're going to kind of let you have a little bit of both. We're going to, in order to save memory, because you're probably not going to use all of the, the HART variables. We're going to let you choose. Normally, you're going to use 1 variable, 1 extra variable. Maybe there's a temperature or a quality code, like a reliability factor, a totalizer function, something like that. You really just want 1 HART variable. So Siemens said, we're going to go through and give you a configurable 4 variables across all modules. So you can pick from channel 0, channel 1, channel 2, channel 3. You can pick anything. So you can pick all 4 variables from one channel. You can pick 2 from one, 2 from another. You can pick 1 from each, whatever. Like, you can mix and match. And then those variables get put in as a real value to the process image table. Oh, that's not my music. That's sorry. I was like, what is that horrible sound? It's somebody actually doing real work in the rest of this building. So they give you the option to put 4 variables and actually put them into your process image table and make them available as standard IO. All of the other data that is available in this HART module is available through data records. And I'll probably go into this a little bit more later, but I had a trouble choosing between the best way to create my block, the easiest configured way, because frankly, if you have in your process image table, you have these four addresses that you could just put in, and you could just use those. And I'll talk a little bit about some issues that come up with building your blocks later when we actually get to digging into code. But know that there are 4 configurable variables across all 4 modules that you can bring into as standard inputs into your system. So they show up just like a real value that's getting brought in. So otherwise, you have to use data records. If you're not familiar with what data records are, look up. There is a video that I put out about the RDREC data block, or not data block, function block. And that is a Siemens thing talking about data records, and it tells you how to use that block. I probably won't go too much into it, but we definitely will be using that in this thing. So welcome in everybody that's coming into the stream in the middle of the stream. It's great to see everybody. And also I see Mika is still holding down #1 in the top fan. So good luck to all the chatters. It's great to see everybody. Got some longtime members, some newer members, and some longtime contributors to the channel. If you're not aware at this point, we do have a Discord server that is honestly, it has a lot of a lot of very good information in it. Just put it that way, because I went through and I think we're up to like over 220 members in the Discord server. Got a ton of stuff. Yeah, Mika's throwing up the alpha wolf logo. He's throwing that flex and the orange logo. Mika is one of the longest members, so I'm gonna shout him out a lot. That orange logo means that Mika has been a member for over a year, which is kind of crazy that we've been doing this for over a year and people still care. But yeah, so what we got here, talking about the heart block, is let's go into our devices networks. And again, for the members, the top level membership, you get this archive. I'll make it available after the stream. And then the bottom tier membership gets you this block, this heart block that we'll be talking about. So you might be familiar with our kind of setup that's back there. It's got the PLC, the IO rack, and it's got a drive on it. We're not going to be using the drive right now, but yeah, we can kind of, yeah, it's there. Again, if you're not familiar with the actual IO setup, you do not need this high of a performance PLC to do this, because the reason why I have this technology safety processor is because we do a lot of stuff, and we do a lot of this. Channel was built off of motion control, so I have that TCPU, so you can do technology objects. Obviously safety is very important, and so we have the safety controller, but you don't need this high end of a processor in order to do this. You could run this off the bottom basic processor. Anything that can run the ET200 you can run this heart module. What I'm going to do is, as you can see from that, I was actually online with this, because you can see the fact that it's orange. I'm online. It's sitting back there on the bench. You can see everybody's happy to be there. But I'm actually going to go offline, because a lot of these configurations you really can't configure until you are offline. And a couple of reasons for doing that, but yeah, just know that you need to be offline. We're going to kind of give ourselves a little bit of room so that you can kind of see stuff. And what I'm going to do is actually click on the heart module itself. And if you're not very familiar with Portal, you should know that the properties, this bottom window is called the inspector window. If I hit Control 5, that thing goes away. And if I hit Control 5, it comes back. And there are 3 different tabs in the inspector window. And sometimes after, say, like a download, this info window will be pulled up, and you'll click on this and you'll be like, where are my properties? Where are my stuff? And be sure that you are looking at the properties tab. So let's just kind of go through some of the configuration of this heart input module. And again, people doing actual work in the warehouse. We're over in Atlanta, West Midtown Atlanta, and kind of people actually doing real work. So pardon the progress or that. So yeah, so let's go through some of the way to configure this module. The main things that you're going to do, just like any other input module, you are going to configure the individual channels for the 4 to 20 milliamp. So as you kind of go through, you could feel free to bring one of these into your TIA portal and just explore through these options. But yeah, so you go through and the channel is individually configured, and normally, just a word of advice, like if you're not using a channel, and there's two reasons there's a reason to do this and a reason to not do this. The reason to do this is it lowers your it just kind of lowers your processing, it speeds up everything, it kind of makes everything a little bit more a little nicer processor wise. But it also, by deactivating the channels that you are not using, it just saves a lot of processing power. The problem is if you ever go back and want to add in a sensor into this, then you are going to have to do an offline download, and this will be a hardware download, and it will have to stop the PLC. So it's kind of a catch-22. If you think that you might want to add in an analog sensor in the future, probably just go ahead and enable that here and then set up for what you would want it to be, because otherwise you're going to have to stop your processor to make that change. I'm going to try something real quick. I noticed, pardon, there, that's better. I keep waving around and like looking at the camera, and I realized that, oh, you're looking at the workbench. So we're going to be looking at some of the options available to us on this HART input module for the transducer that we have over here. So these diagnostics are the built-in diagnostics that will be available for you to use. They'll show up if you right-click on your processor and you go to diagnostics. Let me show you. We go online first. And I right-click here. It doesn't like something, so I say, or I can just double-click on this little thing here, and it'll go up into here. So I'm going to go into diagnostics buffer, and it will tell you these diagnostics. And yes, you absolutely can bring these into your PLC. You can display these diagnostics on an HMI. These are the built-in diagnostics that are available to you in the 1500 processor. These are amazing. They tell you a lot about the system. And so because I have this wire break, it seems like 924, that was me messing with it. Okay, never mind. So go through and definitely set up your PLC time and date and everything, because it could tell you, all right, this is all the stuff from me messing with it yesterday. And earlier today, remember when I was like, hey, something's messed up, like it's crapping out? This was when I moved it. It said HART analog input current saturated. And it's like, wait, what? So what does that mean? Oh, it was showing over 100%. So it was above that 4 milliamp signal. Sometimes these messages are not as, I guess, intuitive. They're a little hard to interpret, but that's what they pay you for, is to interpret the like weird messages. So let's go back to our module here, and here's some of the diagnostics that we have. So I have turned on wire break and HART diagnostics. So HART is actually getting the the communication diagnostics that's set up on this actual device that's back here, it's set up on that to communicate. So those heart diagnostics are communication signals coming from over the heart. And so it'll say heart device, and then it'll give you the message. These other ones, like no supply voltage, sensor supply, overflow, underflow, wire break, all of those are available on your standard analog input module. For example, if you don't have a wire break, then you're just going to have an underflow, or sorry, you're going to have a signal that shows your underflow signal. Usually it's some sort of negative whatever, because it won't have that power. But here's a couple of different things. Like what is the difference between a no supply voltage and a wire break? Oh, well, a no supply voltage means that your power going into your actual module has crapped out on you. So you still have power coming back and forth to your IO rack, but that module itself doesn't have power. That's totally different than if your actual analog input module wires, or sorry, the wires going out to your sensor have broken. So, and those can show up just on your HMI. So on your HMI, there's a page that says, hey tech, go look at this sensor, that wire's broken. And so that's what these are. So the second thing is the measurement type. And on this one, HART is only on 4 to 20 milliamps. If this was a standard module, you would have a couple of different options depending on the module that you have. So there's two types of analog input modules, like the standard types. You have your I's, which is just your current, or you have your IUs, which is voltage or current. So this is where you pick. On a regular analog input module, you could say, all right, is this a 4-wire? Is this a 2-wire? Is this a externally supplied 2-wire or externally supplied 4-wire? All of those options are available to you there. This smoothing time is a built-in averaging system. And there's 3 levels. There's weak, medium, strong. This is going to essentially delay the update of your values, because it's not quite like a running average. It's kind of like averaging out the time. In the manual, it does talk about it to like what these particular values are, but it's taking the time slices and slicing up those times and taking an average over time. So this isn't like a running average. It's an average over a time slot and then presenting it to you. Averaging over a time slot, presenting it to you. So that strong value, you can sit there and watch it update. Like it's not bumping all around. So normally if I'm going to average something out, I put a week smoothing on it if I have issues in my process from it. If you're in the US, you want to use this the 60 hertz interference suppression, because if you've got some sort of ground loop in your conduit or something like that from your medium voltage switchgear or whatever, that's going to come through. In the US, it's going to be 60 hertz. You have options for 50 hertz and 10 hertz. 10 hertz is probably something significant that I'm not smart enough to know about. But if you know why there's a 10 hertz option there, put that in the chat or put it into a comment, because I don't know. And then this HART function, the default is usually correct on this HART function. You can enable and disable the HART functionality, and with that enabling and disabling, it kind of gives you a couple of different options later on that we're going to talk about. So we're going to get to, so this IO address space is what I was talking about before, the process image table. So this is what is available to you just as standard tags. So if you want to address a tag just straight from kind of your program, this is what this is. So these analog inputs will start at address 24. And the way this memory address space is broken up is that your 24 is your first analog input. And so that's a double word. And so that's a 0 to 27648, whatever that value is, because there is an overage. But so it goes into a double word. So that goes into 16 bytes. Say that. No, it's a word. 16 bytes. Double words 32. 4 bytes. Chat. My goodness. I'm gotta slow down. This goes into a single word, which is 2 bytes. So 16 bits. I will use all of the correct words eventually. A real value takes up 4 bytes, whereas a word takes up 2 bytes. So you have all of your analog inputs, which are words. So you have 24, 25 is channel 0, 26, 27 is channel 1, 28, 29 is channel 2, 30, 31 is channel 3. So those are your 4 just kind of percent value regular analog inputs. That's what those are. But you say, obviously there's a lot more addresses here than just up to byte 32. And if you're unfamiliar with kind of like memory address spacing, you don't really have to know too much about that, other than the fact that you are starting at these addresses to get that value. So if you wanted to address the value of this input, then that's there. In TIA Portal, there is a little bit of a cheat code, and the reason I say you don't really have to know, because in TIA Portal there is a cheat code for every module that has these kind of standard address spaces. You have what's called IO tags, and so you don't have to know up front what the offsets are. You used to have to do that. In Siemens, you would have to know, okay, my second channel 1 is going to be on input word 26. But if you flip over to the IO tags, then you can see I've already brought in this test level, which is input word 24, which, by the way, 24, best number in the world. 24, rep to 24. That was my football number in high school. So yeah, all state running back. But so input word 24 is your first analog input. Your second input word is going to start at input word 26. And so in Portal, you can just go in here and create your tags here, and it will bring them over into your PLC tag table, your default tag table, and you can select which tag table to put them in. But you can see I've got a bunch of stuff up in here. Don't look at the handwheel stuff. That's not for this lab. For a future lab, maybe. So you can see this test level, and I made that there in this here. So the last thing is like, okay, Jason, there's a lot more input addresses there than that was in those IO tags. Yes, that is your actual stuff that's in these HART tag settings. And so what I have done here is made available. Since I only have one channel, I could go through and set up all 4 variables. Remember, I said you have primary variable, secondary variable, tertiary variable, and quaternary variable. I definitely knew that. So you have all of those, but the primary and secondary variables by default are set up. They're like they're the linear percent, and then maybe like the distance or something, and I like on this, and so I didn't really find those interesting. The tertiary, I believe, was the quality factor, so like the reliability, some reliability number of the actual reading, and then the quaternary is the temperature of the electronics. And I noticed it kind of gets hot just existing, so it's kind of a you wouldn't be able to use that as like an ambient temperature, but you would know that, oh, hey, it's hot there versus it's not hot. That's about as good as that is. But I want to point out to you that these addresses here are start at 32. And so I went back and kind of like talking about our regular address space goes at 32, or it went up to byte 30 and then 31. So the next available is 32. Now, if you notice, these are taking up 5 bytes each. And what that is you have the 4 variable. So like this is a real value. So it has to take up 4 bytes for the real. And then it has a quality code, and it's got some diagnostics for 1 byte. So you have those 8 bits there that are available to you for the quality of that HART variable. You're like, cool, Jason, that's awesome. And it is. It makes it to where I can make a tag, like in my tag table here, I can make a test level reliability started at 32, and then a test level temperature and started at 37, and it works. So we can kind of go online and look at this. The sounds of, I don't know what that is. It sounds like a bandsaw or something, or a belt grinder. So this test level is the pure input. So that's coming from that input word 24. And then I could see my I double, because it's a real, coming across as 1718. And so I'm guessing that I might have changed these. I might have changed these variables, honestly, on it. But, and then the temperature is around 81, and that's in Fahrenheit. And it's not 80 degrees in here. I would be sweating. So that's what we have there. And you're like, all right, that works. That's great. That's easy. And it is. The problem is if you try to go and set up a single data type, like if you're familiar with the channel and you're familiar with Siemens, you know what PLC data types are. They're kind of the UDT of Siemens. If you go and set up this data type, this UDT, and say, okay, I want because I think I still have mine here. Yeah, so like HART channel data. Okay, so you have this sort of setup here. You have your real value, your byte value, your real value, byte value, real value, byte, real byte. And you would think, okay, that works, Jason, right? Yeah, that's awesome. And I'll be real, in Siemens, so in Semantic Manager like V5, so pre-portal, this was fine. And this would work. And it was easy. And this, you could point this HART channel data to address 32 and then populate it, and it would be right. The problem is when it actually interprets this, it doesn't take it as a byte. It can't take it as anything less than 2 bytes. And so it can only take it as a word. So it offsets everything, and it drives you crazy. So if you're using one of these, you have to manually go in and create your tags. And here's where we come to kind of where I kind of got driven crazy. I guess it wasn't yesterday, it was Wednesday when I was going through setting all this stuff up. And whew, chat, I love you guys. I go through a lot for you guys because I fixed it. And the block takes care of this, and it gives you the data. And because I was trying to say, oh, well, I just want to create a good data block. I want to bring in my hardware ID and parse out the addresses from that. Not so simple. So I don't actually use this because it doesn't work, because portal. Siemens, if anybody from Siemens is watching this, why? Sorry. All right. See, this is how you know that I'm not a complete, total, just like Siemens simp, because I will call out Siemens for their bad behavior, and this is the bad behavior. I'm sure that there's some German reason why, and there's a German person that's sitting telling me how I don't understand something because I'm a dumb American, but that's stupid. That's stupid. You made your own card output 5 bytes, and then you don't have a way to create a UDT that uses it. Maybe I'm just too dumb and didn't find it, but anyway, I'll stop. I don't like complaining. I'll do it. Like, if you want me to program it, give me access. I'll do it. I'll work on it. I'm a solution provider. Let's go back to the real world and let me get off my soapbox. So you have these setups here. Okay, so if you want to use address 32, if you want to use address 37, they're perfect. They work. And honestly, here's the thing. If you had as long as you don't go over 2 of these, this little this thing. So like this works. So like this first part, so like this would work because you're going to get the low byte and then it's going to chop off the top byte and it's just going to ignore it. But then the moment you go to the second one, it doesn't work. So you can create a PLC data type for this, but you have to point it individually at each address. And maybe that's the dumb American part that like, oh yes, you could just do this. But yeah. So the 32, 37, 42, that's the easy way. You can just bring those into your tag table, use them real simple. You can address them directly from an HMI using direct memory addressing, like all of that, perfectly fine. It works. Now, we're not about doing things the easiest way, are we? No, we're about doing things the right way. We want to create software that we can use later on. Now, which, by the way, if y'all don't follow me on LinkedIn, look me up on LinkedIn. It's just Jason Watts. I talk about chicken poop all the time. But also, I argue with people about code portability. And a lot of other people that use other manufacturing or other manufacturers' devices, they aren't inherently in the portable code mindset of, hey, I want to use this code that I'm writing next time and not have to rewrite my code. And so what we want to do is, I want to show you 2 little code blocks that I have. So you may not be aware, but the company that I do work for it but Alpha, my company, I'm the CEO, founder of a little automation company called Alpha Industrial Technologies. We do a lot of agriculture work, among all sorts of other stuff as well. But I have these level sensors in a lot of like storage silos and storage bins. I'm about to sneeze, sorry. Excuse me. Sorry for your ears. And so this is the block that I use to sequence out everything. And it brings in that analog input, and based on that analog input, configures everything out to where now all I have to do is to bring in my analog input, connect it up to my level input, and then it gives me the values that I'm needing to use elsewhere in my program. Instead of having to cut and paste and change variables and shift stuff around, add in tags, add in all this stuff, all I have to do on a system is go through and define all of my inputs, define all of my outputs, and then use my blocks. So this is my standard level block. And so what you have here is my raw analog input. My raw analog input, and then it's outputting the level in percent. So the reason why I choose to do things in percent instead of actual value is because percent is intuitively, like, you get it. You know if you're about to overfill a bin if it's at 85% or 90%. You know that bin is getting full. But if I tell you, oh, it's 4.6 meters worth of material, okay, now I have to remember, how tall is that bin? Is it 7 meters or is it 10 meters? I can't remember. So that's one thing. Like, if somebody for some reason wants something in an actual value, and this is the same thing true for amps on a motor. If you want to be able to use your block, like, actually for every application, you can't have an actual amp output, because that block, that motor might have a FLA of 20 amps, or it might have an FLA of 200 amps. And so the drive outputs percent, and then you can change it to whatever you want. Now, you can have your block if you want to, which I have in my motor control block, or some of them. I have an FLA for the motor so that it gives you an amp output. But once it goes back again, it's like, all right, this motor's pulling 40 amps. My gosh. Okay, wait a second. How big is this motor again? Because 40 amps on a 40 horsepower motor is almost full load. 40 amps on a 200 horsepower motor is the magnetizing current for that motor. So, like, those two things are totally different. But if you go in and you use the percent, you put it up there, and that motor's running at 40 amps and it's 10%, you're like, oh, okay, I'm good. It's just magnetized. It's not even pulling any load. Or 30%, all right, whatever. And you could go from there. So all of that saying, my block outputs percent. So the way I have this set up is it is outputting, I want to say it's like 28 inches. I could probably look up, like, it's set off at like some distance away, and it looks like it's about that far from my vise that it's hitting up again. Yeah, so it's about that far away from the vise, and so if I had, it might be like 100 inches or whatever. I don't know. And so it's saying that it's 71% full. And now remember, that's going from the bottom up. So the longer the reading, the less full it is. So that reading goes down. So logically, that logic has to kind of be inverted on a silo, a level sensor. And again, that's all configured in that VEGA sensor. So that's for the regular analog input. That's the best way for it, because you set up your channel, you bring it in, you scale it, you do your stuff. HART is a little bit different. So what I ran into, because of the aforementioned nuisance that we shall not go back to, yeah, Lucid brings it up. Percent is portable and alliteration is awesome. And so, oh, and Lucid just took over number one. So percent is portable, and right, so we want to create portable code, and not all code has to be portable, but if you're going to use some sort of code that, and you want to do a certain way, why not make it portable? So this HART mod data block is as portable as I could get it. And because what I ran into is being able to, I had the choice of, do I want to make it to where you have to configure those variables, or do I want to make it to where you just pick your channel number in this block, and it goes through and automatically says, hey, this module, I want this channel number, and it gives you all 4 variables. So I went this way. I could have gone through and probably figured out a way to get around the aforementioned problem with the address space, and you could have pointed it, and I could have pulled it out of the hardware IO or the hardware ID there. And one thing I want to tell you, if you are unfamiliar with Siemens, what you have no idea what this hardware ID is, this 274 number, and where to find it, where to get it. So let's talk about that for a second. Inside every single hardware device, what you have is a system constant. So if you missed what I did, I went to the inspector window, under properties, I went to system constant, and I'm clicking on the different modules. So my interface module, my HART analog input module, and now my the position submodule, the encoder input. And what this is a way that you can reference all of the IO, all of the address space, anything that you need from that's associated with that module. There is a way to get to the process image table from that module. And not even the process image table, you can use that hardware ID to get to its data records. We're going to use that here in a second, because I ended up deciding not to use the process image table portion of it. I ended up using the data records portion of it. And so in the block that I did, I'm actually using the data records, and this is gonna look, when I open up this block, you're gonna be like, Jason, you're a moron. This took you like this was difficult for you? Let me explain, chat. All right, here we go. I'm being vulnerable to you, chat. Don't flame me. Yeah, I'm without risking being like what's the pirate software? I don't know if y'all are into that drama stuff and some of his code. This was the best way to do this code, I promise you. So what you have to do, so what I started out to do, let me explain to you what this does, and I'll explain to you why I do this. So what this does is it uses the read record built in. I think it's special function 83 or something like that. It uses the read record block in order to pull data record 121, I think. Hold on. I thought I had it pulled up here on my thing, and I was going to be fancy. Yeah, it's 121. Chat, why did you let me embarrass myself like that? It's right there. So the index number is the data record, and the M length is the number of bytes that you were pulling. So in the ET200 manual, it goes through all of the data records that are available to you in the HART function itself. And so let me pull this up because I wanted to show you. It's on page 59, if I remember. Sorry, pull this up for you to actually show. Woo. The one problem with this, never mind. One problem with this, this manual is it doesn't necessarily give you. It's a bunch of manuals like piled in on top of each other, and so the appendix. Yes, here it is. So swap over to this real quick. So this big manual is a collection of manuals, and it has all, so like in the appendix for the manual for the analog HART, the analog input with the HART module has all of this information for all the data records in it. And blah, blah, blah. What I was wanting to show you was how this is actually set up. HART variable data records. Finally, finally we made it, chat. So again, we have the same issue that we have in the process image table. We have 4 bytes for the value, and then the 5th byte being a quality code. And then you start over. And so every module takes up 20 bytes. But if you were to just pull all of this as a block and put it into a UDT, the UDT gets interpreted goofy, and you can't just pull it over into it. So what we've done with this block is a little bit of a trick. And so it is kind of a little fancy, but what we have to do is we have to bring our data record, because one thing about data records is you pull over a block and it's a bunch of bytes. And just like we saw in the manual, it's a bunch of bytes. It's 80 bytes for all 16 variables. It's 80 bytes, and we get 16. All 4 channels. It's 80 bytes because it's 20 each. So bring this thing over, but we can't immediately layer in our data types because of that weird thing. So what we have to do is we have to bring everything into a data buffer, and then we have to name our tags very specifically. We have to point them to particular pieces. And this is the only way that I could do it. At chat, like if y'all come in and if you're watching this like 20 years in the future and it, like whatever, this has been fixed, this is the only thing that I could figure out to do it. And I promise you, I spent hours trying to figure out different ways of doing this. And this isn't my first rodeo. I've got a couple of years of doing this stuff. And so what I had to do was bring everything into a big buffer. So an 80 byte buffer. And if you're kind of new to Siemens and new to programming, probably you're going to glaze over on all this stuff because this is pretty intense stuff. But I brought everything into a big 80 byte buffer. Cool. I got my data in, and that is doing this here, that read record. Now I have to parse my data. And of course, I'm swapping. I like to use ladder just because visually for these streams, and a lot of times if you're used to ladder, you're just kind of like looking at it. But then there's some things that ladder does not do well, and that's modifying data, transferring stuff, just saying, hey, this equals this equals that. So I swap over to an SCL block, and I know Lucid loves it when I do this. I know he loves it because his code has all of these little nuggets in his plant of random blocks of SCL. And so what I've done is all I'm doing is saying, okay, I'm going to take these 4 bytes. I'm going to take these 4 bytes and then make it into that value and then transfer it. And so if you notice, all I'm doing in my SCL is taking bytes and moving it into a smaller byte buffer. And then I'm just taking and moving this to my output. So my channel PV, so channel PV, SV, PV, QV, those are my outputs. And you're like, Jason, so you're not really doing anything because all I'm doing is moving this value. There's a trick in TIA Portal called overlaying. If you have a memory area in the static memory, there is a way that you can take that, whatever, how many bytes it is. If you want a word, if you want like an integer, and you want to pack in a bunch of bytes, and you want to send it across as an imager, an integer, you could pack in a bunch of bits by having a single word that's overlaying a bunch of bits, and then you fill in all of those bits, and then it gets overlaid into a word. That's what I'm doing here, and it's up in the actual interface to this. You notice I have my big module, or my big buffer, which is 80 bytes, and PV data buffer is a buffer of 5 bytes. Cool. And so what I'm doing is I'm going to take all of the 5 bytes in that buffer and just move it over. And that's what I'm doing down in the SCL. But I'm going to do what's called overlaying, and I'm going to overlay a real value on the top, starting on top of that PVDB. And so I've got that extra byte, and I'm taking and overlaying a real value here, and it's taking those first 4 bytes and it's making that real value PV value. And you do that by, when you set up this, first of all, you have to have an optimized data block. None of this overlaying doesn't work in an unoptimized block. So in an optimized data block, set up your value, whatever you're going to overlay, and set it to set the retain, say set in IDB. It has to be that way. And then when you come in, directly below it, make your value of whatever it is. So I named it PV value. And before you select in real, you type in the word at. And I'll show you, I'll do this down here. I'll delete it here in a second. So I'll make a new row. Hold on, no, I'm not gonna do it. I don't want to blow up my block. Because I will do that. So this PV value, when you go in here, you just type in at, and you select it and hit enter, and then it automatically fills in this little part here. And it automatically fills in at PVDB, because PVDB is whatever's above it. So instead of typing real, you type in the word at in the data type. And if you don't have this set in IDB set, it won't do it. When you type in at, it'll just be like, what the crap are you trying to do? And so you type in the at, hit enter, and it will fill this in. And so now it will actually go through, and even though that's 5 bytes, it will go through and overlay the first 4 bytes with that real. And so because there's enough space, it allows it to go through. And then what I do is, all I'm doing is taking that static value, which if you're familiar with Siemens function blocks, you know that you would be able to go in and directly access that PV value. You would be able to access that. So in this one, I think it's named, so like if I wanted to access this of like a move block, bro. Yeah, that's what I want. So if I wanted to, I could go to test heartmod.pv value. Say that. I guess you can't. Oh yeah, that's why I did this. I lied. I'm a liar. Wipe out everything that I just said in about the past 2 minutes from your brain. An overlaid value cannot be directly accessed. It does not have global access. It only has local access. So that means that this little line here, where I take and move and set my output to that PV value, that is necessary. And so what I did was, all I did was went through, and for each one of these values, I have an offset. Again, remember, I have an input that's the channel number. I just have an offset. So like whatever my channel number is times 20 plus 5, and then I'm moving all of those bytes over into those the smaller byte buffers, and then overlaying a reel on top of that and moving that reel out to it. And it sounds complicated, and I know how I would have done this in Classic Portal. This is how you have to do it, and it's obnoxious. And so what I could have done is so here's a little bit of inefficiency in this software. If you want to pull 4 channels, it is pulling 80 bytes each time. So out here, I could bring this block in, and excuse me. I could bring the block in. Bro. Portal sometimes. Portal things. So if I wanted to change to channel 2 of this, which is disabled, all I would have to do right now is modify this. I guess I could just double click here. So modify this to 1, and it pulls up it parses out the PV. Obviously that channel is disabled, so that's what you would expect. So if I wanted multiple of these, I would have to have one of these blocks for each of my channels, which, yeah, that's not quite efficient, because each one of these blocks, every time it goes through, it is going out and pulling 80 bytes of a data record, and then technically only using 16 of them. And so that's kind of where this block is going there. By the way, when y'all get this block, feel free to go in and mess with stuff, because you technically have access to the quality, the QV byte, through this method. So I'm only pulling over 4 into this little data buffer, but if you wanted to pull, so it'd be 0, 1, 2, 3, 4, so like 4, so byte 4 in this data buffer is PV's quality value, or it's its quality code. Let me see if there's close here what the quality, if it has a quality code thing. It tells you basically, yeah, it's in the manual. I'm starting to sound like Siemens guy. I am a Siemens guy. It's in the manual. Look up the manual. Yeah, this overlaying, which, by the way, there is a thing about overlaying, a video specifically about overlaying where I talk about this, but this is one of the things, one of the tricks that you could do with overlaying, and I fought forever on doing this. Just loop through the data record. Yep. Yeah, I think SoulStep, were you the one that actually originally was using this HART module that we worked through? Because honestly, this came, I can't remember who it was, but it was someone in our Discord that actually brought this up. And I was like, okay, here, I brought the stuff in and showed how to bring in those different variables, and I didn't really go into it very much. And it sounds like SoulStep went through and actually did kind of the same thing. And yes, you can absolutely go through and set up your code to parse out all of these individual. Yeah, so it was SoulStep that created this stream inadvertently, probably 6 or 7 months ago. I'm very timely in my videos, but yeah. So what you could do is you could pull out that quality value, and you could also make it one block to where it has all 16 variables on the output of your block. You could absolutely do that, and then just kind of duplicate this. I honestly was like, most people, if they're going to be using this block, I would see myself using it for one channel, getting the variables, and then using them. And yeah, I mean, the extra byte pools in this, I don't know what type of processor like load you would get. Like, it would hit, you would get a processor hit, but I'm not sure how much it would be because of that extra 64 bytes or whatever that you're, no, 54 bytes that you're having to pull. Not a lot. Like, that is like one TCP packet's 100 bytes, and that's like less than a millisecond. So anyway, I don't think this is very extremely inefficient, but there is that inefficiency if you're really tight on your resources and you're having to pull a lot of HART variables. Honestly, if you're having to pull a lot of HART variables, you're probably going to write your own code that does it more efficient if you run into efficiency issues. But the framework's here. This is, I mean, it works, as you can see. And I can go in and, like, on the VEGA app, change what these variables are connected on the back side, and they just automatically come through here. So that is the block. How long was that stream? About not quite an hour and a half. So that's pretty good. That's pretty good. An hour and a half of good content. And so this has been kind of an overview. And as you know, we're about to go into the kind of free chat portion of the stream. And if you're watching this within the first week, then I probably won't have had time to edit it out. No, I keep the last portion, the free chat, open for a week for non-members, and then we're gonna cut that out and then give that as a separate chat area for the members. So hang around if you are here in chat. But this is the HART block. This is the HART data. And yeah, if you've got a comment or something that like, hey, I missed something, what's this question? Drop a comment. I'll either answer it or I might do a short about it. But as always, if you've made it this far, I mean, come on, why haven't you liked and subscribed? I mean, like, if you can listen to me for an hour and you haven't liked the stream and you haven't subscribed, that's just crazy. But in all seriousness, liking and subscribing really does help this channel out. It helps get out there. The more you like this video, the more the content gets out to other people that might be stumbling across how to use this HART block. I'll do my job and get all the metadata and like all of that stuff and to be able to optimize for it. But yeah, liking and subscribing really does help. Also, I mentioned it earlier, we do have a Discord. Be sure, if you use Discord and you feel kind of like isolated in your automation journey, there's over 200 of us at this point that will sit there ready to help you out. We're all growing, we're all learning. That description or that link to our Discord server is in the description of the channel, and I think it's in the description of this video. Yeah, I think it is. And as always, if you didn't know, the memberships that are available for this channel are, yeah, what you would get at the lower tier, the supporter tier. You're gonna get this block. You'll get an archive file that you can open up in TIA, and you will get this block. You can play around with it. With the programmer level, you get the whole archive, or you get the whole project archive. I'm just gonna upload this whole thing, so you have all the code, all the other stuff. Yeah, this other block, I think it has a password on it, but whatever. You can see how everything works, the configuration. You could play around with it. That's that available. Also, all members get access to the members only video and the stuff that I trim off later. But for right now, this is what we've been talking about, the HART block. And you're gonna fade out. If you're here live, we're gonna continue the stream for at least I don't know, at least 30, 45 minutes, maybe an hour. However, if y'all got questions and stuff, y'all start asking them. But otherwise, yeah, I'm just going to ramble on. But yeah, thank you for coming in, and we're going to swap over to the free area. So check it out next time. And yeah, peace. Always be learning.